a linear algebra approach to the virtually Abelian isomorphism problem. I'm a PhD student at UTS under Murray, who was around earlier. He has since dipped, but yeah. Okay, so I'm going to start with a linear algebra structure. There is a group involved, so everyone can relax a bit. We're given a finite group, H, of size K, and we're also given a list of matrices. The list of matrices follow the structure of K, but is not limited to the structure of K. What does that mean? It means, for example, if I gave C6 as H, then I could certainly have a list of matrices at the bottom here. X1, this list, this subgroup of GL2Z is a C6 subgroup. But I could also have the second list, which is actually C3. And I could also just have a kind of arbitrary weird example, which is just the identity 6 times, because the identity 6 times follows the structure of C6, but is not necessarily limited to the structure of C6. Okay, so now I'll present you with a problem to solve for such a structure. So if I'm given 2 of these structures, this isn't anything crazy. This is just a conjugacy problem, a simultaneous conjugacy problem. It asks, does there exist a matrix in GLDZ such that I can solve the simultaneous conjugacy problem? So in the 3 examples I gave earlier, the 3 lists, since the list of matrices generated C6, C3, and were just the identity 6 times, then clearly no such solutions exist. But I've also included 2 additional lists just for the purpose of the example to show that such solutions do exist. Nothing crazy. And I will also present, so I'll be presenting 3 linear algebra problems. This is the next one. Given 2 lists of vectors, and again, a group H, we ask, for these 2 lists of vectors, does there exist another list of vectors such that I can solve these list of equations? So the H structure doesn't necessarily act on the list of vectors, but you can see here that in my solution, this last vector from my solution is dependent on the structure of H. So in a very simple example, let's consider C2. It means I'm just solving a list of equations, essentially. And somehow they cancel, but they cancel differently depending on my finite subgroup H. So in this example, you can see that U11 and V11, U12, V12, U21, and V21, they all differ by the same vector. This, again, is not anything crazy, but we can combine these 2 problems, and it gets a little bit more, I guess, harder to solve. Given 2 of these finite structures and list of vectors and a list of matrices, we want to solve the simultaneous conjugacy problem, but we also want to make sure the solution to the simultaneous conjugacy problem, this M, performs a linear transformation to one of my list of vectors, and also my second list of matrices that follow this H structure performs a linear transformation to one of my solution vectors. So straight away, I'm not going to give a full explicit example for this, just because C2, you already presented with 4 equations. So at C6, you would get 36 equations. But straight away, you can see this changes slightly because the cancellations are now different. You can still cancel depending on the structure of H, but it's really dependent on the structure of H. So I know this is kind of like a random linear algebra problem. And I guess this talk will be seeing how we get to this linear algebra problem. Okay, so now pivoting back to the isomorphism problem. The isomorphism problem essentially asks, given two groups and their finite presentation, are these two groups isomorphic? A very natural problem from my point of view. It's an obvious thing to ask if two groups are isomorphic. And we will be working with strictly finitely presented groups because from the input side, infinitely presented groups presents, let's say, difficulties. Okay, so we know that the isomorphism problem is not decidable in general for finite presentations. In fact, it's not even decidable for any subclasses because the natural progression after knowing that it's not decidable in general is to look at subclasses. The focus for us will be virtually Abelian groups, but we take inspiration heavily from virtually free groups and polycyclic-by-finite groups. So we know that it is decidable for these groups and others, but these are the large results, I suppose, in this area. And work has since shifted towards finding complexity for such isomorphism problem algorithms. So recently, virtually free groups was found to be solvable in p-space. And I'm not really going to go into detail about what p-space is and the actual complexity, but essentially we're looking to find bounds on our known to be decidable problems. And in the finite group space, it's a completely different game, I suppose. In general, it's solvable in quasi-polynomial time, which is somewhere between exponential and polynomial. And then they also look at, finite groups in terms of specific subclasses. So the main point is that given arbitrary presentations, we don't necessarily have a complexity bound. In fact, in order to get a complexity bound, most of the time, not all of the time, you require the presentation to be given in a specific way. And I will talk about that a bit more in a bit. Here are some of the references if anyone's interested. But yeah, I won't be going into detail about that. Sorry. Okay, so virtually Abelian groups, I'm just going to tell you, is a subclass of polycyclic-by-finite groups, which is known to be decidable by Segal. And I guess I'll just talk about why I don't use Segal's algorithm a little bit here. So point one, polycyclic-by-finite groups are known to be residually finite. That is, any homomorphism from such a group into a finite group maps only the identity to the identity. Okay, so in Segal's algorithm, he calls the solution to the word problem. The word problem asks, given any element of the group, is it the identity? So his algorithm for solving the word problem is as such. It's two recursive algorithms running simultaneously. And usually when we have two recursive algorithms running simultaneously, we're already a little bit sketch about the upper bound complexity. So his solution to the word problem is construct all finite groups one at a time. So already, yeah, it's a little bit difficult to do with the complexity bound. And then for each finite group, he finds a homomorphism one at a time, checks the word, see if it maps to one. If it terminates, we stop the first procedure. At the same time, we essentially run consequences of the relators given because our group is finitely presented. If you'd like, you can think of this as TC transformations. And the second algorithm terminates when we get G, we get our word back. So if our word is not the identity, then the first one will terminate at some point. And if our word is the identity, the second algorithm will terminate at some point. So we know this will terminate. As to when, unclear, because TC transformations, you don't really have a stopping point, I suppose. And at the same time, constructing all finite groups and checking them one at a time, and then checking one. Yeah. Anyway, I wouldn't really know how to find a upper bound complexity for such an algorithm. And that's just the word problem. He calls this multiple times in his isomorphism problem solution. Okay, so because of that, I guess we started a smaller subclass, virtually Abelian groups. A virtually Abelian group is a group with a Abelian subgroup of finite index. I like to think of it as just a group where you can partition it finitely many of times as a free Abelian group. This is an example. I won't really be going into too much detail, but it is there if you want to have a look. And now I'll just talk about extensions quickly. This is just a quick reminder for anyone that's familiar with extension theory, is that we can break any group into a normal subgroup and its quotient group, and we call that a n by q extension. And we say a group is x by y if it has a normal subgroup that is property of x. So a polycyclic-by-finite group is got an n, a normal subgroup that's polycyclic, and its quotient is finite. So we know that any virtually Abelian group, you can find a normal subgroup that's also Abelian, and by extension, free Abelian. So really, we're going to view virtually Abelian groups from the lens of Abelian by-finite groups. And that's also why Abelian by-finite groups are, virtually Abelian groups, which are Abelian by-finite, is a subclass of polycyclic by-finite, because any finitely generated Abelian group is polycyclic. And we're working in the finally presented space. Right. As I mentioned earlier, in terms of working with complexity, usually we want our presentation to be given in a specific way. This is so we can find upper bounds for certain algorithms. It's not to say you must always do it this way. For certain subclasses, you can give arbitrary presentations, finitely generated. But in this case, our presentation is heavily motivated by the presentation given for virtually free groups, which was seen to be in p-space. Okay, so there's a lot of stuff here, but essentially we're given a virtually Abelian group as a Abelian subgroup. You can, without loss of generality, you can assume this is a free Abelian subgroup that's also normal and finite index. And then we're given coset representatives. I'm using right coset representatives for such a normal subgroup. And then I'm also given this list of rewriting rules. And the rewriting rules are just a specific way of writing the relations in some sense that allows you to easily shift each element of G into this form of AT, where A is my free Abelian component and T is just a coset representative I tack on at the end. So all of this is just to say I have a very specific way of presenting this group, and it allows me to easily get each element of G into this normal form, if you will. Now, what we do is we take our presentation and we can find all of our extension components. I'm not going to talk about the details of these extension components, but essentially you already have your normal subgroup. You can work out your quotient from your coset representative. This theta thing is kind of like the action of my quotient representatives on my Abelian group. So how it slides. S is a transversal map. So how I get my coset representatives, which I'm already given, so nothing crazy there. And this f function, it's called a two-coat cycle. You don't necessarily need to view it from the point of cohomology, although if you want to, that's also fine. But it's just an abelian group, and it's given uniquely for each transversal map. So it's given uniquely since we're given a coset representative set. And again, this is an example that I'm not going to go into detail about. Okay, so we have our group, we have the extension data for it, and how we work out isomorphism is through equivalent extensions. We say two extensions are equivalent if their two cocycles differ by a two co-boundary. What that means is you can think of it as a equivalence class of up to two cohomology. These are just some words I'm throwing around, but we're given these F1s and F2 explicitly by our presentation. And you'll see later in the algorithm what we're doing with them, but essentially you're just checking they're within the same equivalence class. And we say two extensions are equivalent if there's an isomorphism from their larger group that they create. So this, in some sense, allows us to find an isomorphism. This fact at the bottom here is used in the algorithm, and I'll talk about that a bit if we have time. Okay, so one issue with this approach is that if I find that two extensions are equivalent, then I know the groups are isomorphic. But if a group is isomorphic, it does not necessarily guarantee that the extensions I get for such groups are equivalent. So it only goes in one direction. So I could get two extensions that are not equivalent, but I don't know that the larger groups are not isomorphic. Yeah, so I was thinking about it and I said to myself, so extension not equivalent does not mean not isomorphic. And that was a little bit confusing even to me. But anyway, here is an example. So what I've taken is this group that I've been using throughout this presentation, and I've broken it up into two extensions. So these are both normal subgroups of G. They both generate Z2, free abelian group of rank 2, and they have drastically different coset representatives. So if the quotient group is not the same, then they're definitely not going to be an equivalent extension. So how we overcome this is by using a thing called an isomorphism preserving subgroup. So we let F be an operation that when applied to a group G, we get a subgroup of G. And then we say this subgroup is isomorphism preserving if any isomorphism between two groups will preserve this subgroup. Okay. Another way to think about this is if you're familiar with characteristic subgroups, this is essentially a slightly more general version, whereas characteristic subgroups preserve under automorphisms, this just preserves between relabeling of different groups that are isomorphic. Okay. Most characteristic subgroup operations that come naturally, whatever that means. So think commutator subgroups, which I think was referred to as derived subgroups earlier. The center are all isomorphism preserving. So our chosen operation that we've used is G to the N. This is the group generated by the nth power element. And there are multiple operations you can choose, even in the virtually abelian space. But I've just gone with this one. I've included a sketch of why I can do this, but I'm not going to go into details. Feel free to have a look if you like. One thing I will note that it's quite unfortunate that the abelianization of virtually abelian groups does not actually provide any useful information. So a bit of a bummer there, but Anyway, this now is the isomorphism algorithm for two virtually abelian groups. So we're given the isomorphism, we're given the two groups as our virtually abelian presentation. So we're given a normal subgroup, we're given its coset representatives, and we're given its rewriting rules, as previously stated. We calculate our isomorphism preserving subgroups. So you can think of it as g to the n in this case. And we check if they are isomorphic. Since they're just free abelian subgroups, we just check the rank. And then we check the quotient if they're isomorphic. These quotients are finite groups, so we already know there's complexity bounds on how to check that. And then from there, we construct two extensions. We know we can construct these extensions as previously stated with all its data. And this 0.4 is really where the bottleneck is. From here, we have to find two automorphisms, one on our free abelian portion, which is n, and another automorphism on our finite group, such that the following two things hold. So the first thing is to say the action, the sliding action, these theta things, they differ only up to conjugacy. I guess they equivalent up to conjugacy, more precisely. And the second thing is to say that my two cocycles, after applying my automorphism from my free abelian group, is in the same equivalence class. Okay, so this is a little bit unclear, I suppose. It could be, I don't know. Maybe you're very good with extensions, it's super clear to you. But this 0.4 is essentially what we reduce to a linear algebra problem. And this B here is from my code2 boundary. Again, I'm not going to go into the details about the cohomology group. But essentially, what we're doing is we know that this alpha is from the automorphism group of n, which is free abelian. The n is free abelian. And we know the automorphism of the d-dimensional integer is isomorphic to the general linear dz. General linear dz, yes. So what we do is we just map any free abelian part into zd, and then we map our alpha into some matrix in general linear dz. And since we know the automorphism group of a finite group is going to be finite, we can, in some sense, iterate through all of them with a bound. So then what we have is we essentially transform 0.4, which is the most difficult part of the algorithm, into the linear algebra problem that we had at the very start, where our actions, our theta actions, they go to one of our matrices in our list, and we're looking for, it's written the wrong way around, but you can just times across the automorphisms. And we're looking for this alpha, which is an M. And we're not necessarily looking for the beta, because what we do is just iterate through all of them. And the second point, 4.2, it's a little bit more clear if you write the boundary as these three things. And these three things are just elements of our free abelian group. So they naturally translate into a vector. Yep. Thank you for listening. Any questions?
Thanks for the talk, Jerry. Does anybody have any questions? I guess I can ask, do you have any expectations on the complexity once you get there?
For the linear algebra part, not too sure yet. We know that the simultaneous conjugacy problem is solvable in general. This is a simpler version because we're working with finite subgroups of GLDZ. But it's also a bit more complicated because we have this list of equations that comes afterwards that must be also solved simultaneously with that. The pre-processing, I currently have a deterministic algorithm for the pre-processing, although the complexity might be a bit high. So I'm hoping to find a, I guess, smarter way of doing it. So I would expect it to be in P space as well, at least. But as to the exact algorithm, I'm not too sure at this point.
And if you knew something about the groups, as in they're presented as a split extension or something like that, would that make things simpler?
Right, yeah. So if I go back to the start, so if I have a split extension, that means the co-cycles are in some sense trivial. They don't have to be trivial, but they can be reduced to be trivial. So what I really have is just a simultaneous conjugacy problem because, well, my U's and V's are just, you can think of them as ones. Oh, sorry, zeros, because it's additive, so nothing to solve really. So then I just have the simultaneous conjugacy problem. And then conversely, if my extension is central, then my first point, my list of matrices are all trivial. So then M is trivial. So I'm just solving this list of equations.
Cool.
Cool.
Well, if nobody else has any questions, then we'll thank Jerry again.